Okay, everyone, we're back at it with 3.4. It's page 14 still, distinguishable permutations. This is if you have some objects that have some repetition or that are identical, right? Like in that first one, atom, right? A repeats. If you switched those A's around, you're not going to get a new word, right? But if we switch like the M and the A around, yeah, we get a new word. So the question is, if we have objects that are identical within a word, how many distinguishable words can we make? I would stick to the formula on this one. Let's break that down. So N is the total number of letters. So on the top, it's going to be 4 factorial, right? Because we have 4 letters, A, D, A, and M. And then we have one letter that repeats, which is the A. And there's 2 of them, so I'm going to on the bottom put a 2 factorial. I don't have to worry about the D or the M. I mean, I could put 1 factorial, right? 1 factorial, 1 factorial. But 1 factorial is just 1. If you divide by 1, you're not going to change anything. So the simplest way is just worry about the ones that repeat. So this is 4 factorial divided by 2 factorial. So 4 factorial, 4 times 3 times 2 times 0, that's 24. 2 factorial is 2. My answer is 12. If I listed them all out there, it'd be 12 distinguishable words, not necessarily real words, but different permutations. Okay, so let's try another one. Banana. We have 6 letters, so the top is 6. B doesn't repeat, so I don't have to worry about the B. A, there are 3 of them, and there are 2 of them, right? So I'm going to calculate that out. See, 6 factorial is 720. 3 factorial is 6. 2 factorial is 2. So I'm going to do 720 divided by 12 for that one. All right. 720 divided by 12, my calculator is 60. I want to have 60 permutations, right? So that's how those work. Okay. How about Mississippi? 11 letters, right? So 11 letters in Mississippi. M doesn't repeat. Don't worry about it. 4 I's, 4 S's, 2 P's. Oof, 11 factorial. That one's probably a pretty large number. So that's going to be this guy. And then 4 factorial is 24. And 2 factorial is 2, right? So I'm going to calculate that. Now, when you're calculating this, multiply all that stuff on the bottom first. Right? So that's 1152 down there. And then finally do that division of those 2 numbers, okay? And we got 34,650. Different possible 11-letter words. Okay. Awesome. On to combinations. So on to page 15 here. Combinations is kind of like permutations, except for order does not matter. So no, without regard to order. Order does not matter. Order does not matter. There's a formula for it, just like in permutations. There's your formula. All right, we're selecting R objects from a group of N. There's going to be a calculator function for it, like we've seen, you can Google it, combinations for a TI-84 calculator video, or go to that calculator.net, that page that I showed you, had the combinations calculator that you can use. But here's the idea. Number 8, it says, from the playing cards, we have ace, king, queen, and jack. So there's 4 cards, okay? There's 4 cards in front of you. How many 2-card combinations can be formed? I can do this one just by trial and error. Like, for example, I could take the ace and the king, right? Now notice here, order does not matter. Am I going to write king and ace? Nope, that's the same. Order does not matter. So AK and KA are identical. So don't write the KA, back it up. Oop, backed it up too much. Only AK, Okay, so what other two cards could I put together? I could put together the A and the queen, ace and queen. I could put together the ace and the jack, right? Or I could put together the king and the queen, or I could put together the king and the jack, or I could put together the queen and the jack. All right, let me know, is that all the possible two card combinations? So let's see, we got 6 of them, right? So that means that if I take 4 cards to start with, and I choose 2 at a time, that is equal to 6. All right. I would encourage you to do those calculations using your calculator or the calculator.net feature, right? This formula does work, but typically you don't really need to use it. Just use your calculator, all right? So definitely learn how your combinations feature works on your calculator, or just use that calculator.net. That's my advice. All right, let's try another one then. From the playing cards, ace, king, queen, jack, how many 3-card combinations can be formed? All right, that's 4, choose 3. I could try to list them, but I'm not really concerned too much here listing, as I am just getting the total number of combinations, right? So try 4, choose 3, probably have it all figured out on your calculator now. It's 4. I'd have 4 possibilities. You want to try to list them? Go for it. Okay. Number 10, how many 5-card combinations can be selected from a standard 52 card deck? Oof, I don't want to list those, that's for sure. There's lots. This is a poker example. There's 52 cards in a deck. Poker is usually a 5-card hand. So how many possible poker hands are there, basically? This is, I'm choosing from 52, 5 cards at a time. Order does not matter. It's just a group of 5 cards in any order that I want to arrange them, right? For 54, 52, choose 5. What am I talking about? Okay. 2, 5, 9, 8, 9, 6, 0. All right. So there's lots of different poker hands. Okay. So again, I'm calculating these just with the calculator. You do that too. That's my advice again. Okay. How about, how many ways can you select a committee member of 4 people? 15 people to choose from. 15, choose 4. Right? Why aren't we using permutations here? What happened to permutations? Well, if you're just creating a committee of 4 people, it doesn't matter the order of those 4 people, right? Like they're just a group of 4. It doesn't matter how they're sitting. They're just 4 people meeting together, right? So order does not matter. Therefore, I want to use combinations. One of the keys in this section is just distinguishing between combinations and permutations and which one to use, the C or the P, okay? So this one, 15, choose 4. Use your calculator for that. And it's 1,365. All right. Next, finally, we're going to put this all together and we're going to do some probability questions using permutations and combinations. So number 12, a student advisory board consists of 17 members. So we got 17. 3 members serve as the board's chair, vice chair, and secretary. As soon as they start mentioning offices or assignments of people within a board or a committee, that's permutations. It's because the order matters, right? If one person is the chair and another person's vice chair, if you switch those people around, you've got a new cabinet, you got a new board, okay? So when they specify that, it's permutation. Okay, each member is equally likely. Okay, 3 members are randomly selected and assigned to be the new chair, vice chair, and secretary. What is the probability of selecting the exact same 3 that are already holding the position and reassigning them to their position? Well, okay, so for probabilities, you're always writing a fraction, right? Where in the denominator, it's the total number of possible ways for this to occur. So we are randomly selecting 3 people from 17 and putting them in a specific order. That's 17P3. Choosing from 17, putting them in either chair, vice chair, or secretary. So that's a 17P3, okay? Of all of those possible permutations, how many of them would have the exact same 3 people in the exact same 3 positions? Well, that's only one permutation, right? So the top number here would just be 1. Okay, so that's how that one works. 17, got to do the calculation of 17P3. That's 4,080. All right. Next, the offices of president, vice president, and secretary for a club are going to be filled with 12 candidates. 7 are women. If each candidate is equally likely, what's the probability that all offices are filled by women? Fraction time. Okay. I always like to start with the denominator first. What are the total number of possible ways? So we've got a pool of 12 candidates, and we're doing president, vice president, secretary, 3 people. 12, let's see, P or C? You're right, P, because we're putting them into specific roles. Okay, that's the total number of ways to choose 3 people out of 12 and put them in a certain role. Now, of all of those ways, how many of them have all women, have women in all 3 of those spots? So there are 7 women to choose from. And again, we want 3 of them. So that would be 7P3. That's the total number of ways where we have all women. And if I calculate this, I'll have it. So 7P3 is 210. And 12P3 is 1320. And this one decimaled around into 3 decimal places. So let's take it one step further. 210 divided by 1320 is about 0.159. Okay, so about a 16% chance of having all women serving on the committee. Okay, let's try one more here for this video. You're dealt 5 cards from 52. What's the probability that you're dealt a heart flush? Okay, so fraction time, because it's probability. How many total ways are there to choose 5 cards from 52? It's 52. Choose 5. I'm using C here for this one because order does not matter. Right? Just all you're concerned about is if all the cards are hearts or not. Okay. Now, what's the probability that you're dealt a heart flush? Of all of those 5-card combinations, how many of them contain all hearts? All right, well, we know there are 13 hearts, and we want to choose 5 of those hearts. Okay, so I'm going to do 13, choose 5, and that's 1,287. 52, choose 5. Is that, well, we did that one before, right? The 259, 8960. And it says 4 decimal places on this one. So this one's about 0.0005. Okay. Now, what's the probability that you're dealt a flush? All 5 cards are just the same suit, not specifically hearts. So just multiply that by 4 because they're 4 suits, and you'll have that answer. 0.002. Okay, that's it. Thanks, everyone. See you later.